In this video we're going to learn about vector functions. This is an introductory video, and we're going to learn about what they are, what they're for, and the nature of them. And what is a vector function? Well, so far you might have looked at vectors like, say, vector v, and it could be, if we write in Cartesian form, might see something like that in 2 dimensions. 3 dimensions might be something like that, and that's what it stays as. Once it's defined like that, it stays like that. But a vector function amazingly combines a vector and the concept of a function together. So an example might be vector function r. Now, if that varies in regards to time, which they often do, it's often the parameter we use, it might be described as r of t with the tilde still under the r. An example of one might be something like this example in 2 dimensions. This is just an example. Okay, and certainly we'll see them in 3 dimensions as well. So the value of r changes as time changes. So time is a parameter that changes. And as you can see, as let's say r is increasing, the value inside here is 3 plus t. So as t is increasing, we will get an increasing value for i. For j, as t increases, we'll get a decreasing value for j. So it's not fixed. So it's a bit like the analogy of a constant versus a function, a varying function in regular maths that you're used to before this stage. We can apply the same concept to vectors, and it's very useful. It has many purposes. And an example of the one we've just written here, r of t, might describe particle r. So if r is a particle, okay, we often use that concept of particle because it sidesteps all of the physical issues with things moving around. So it's something that's infinitely small, and you don't have to worry about distribution of mass and air resistance and all those real life things. It keeps it purely as a mathematical simplified model. I use plural, that's singular. R is a particle, and we'll be looking at, this might mean that it describes the position of r with respect to time. And that would be a use of that. That's an example. This one would be a 2-dimensional model. It's important to note that these vector functions they're not the same as Cartesian equations. Although they can be related, then they're certainly not the same thing. You might remember Cartesian is y versus x. Like so, you've seen that. Okay, that's usually some displacement or distance in one direction versus a displacement or distance in the other direction. Okay, whereas r of t is more likely to be the position, the overall position as time goes by. Remember, t is the parameter changing. So it's the position against time, whereas Cartesian is position in one direction versus position in the other. So conversions between vector functions or vector valued functions and Cartesian forms, we're looking at that same example. I've written it down again, and what we do, remember, we're in 2 dimensions we're talking, and basically in general 2 for 2 dimensions. In general, we're looking at r of t is xi plus yj. and the x and y are the Cartesian links. Okay, so that's the link between the vector valued function and the Cartesian form. So to convert this given one here to a Cartesian equation for its path, because that will give the path, because it's distance in one direction versus distance in the other, and that's what a path is. Whereas this vector function is position at a given time. Not the same thing, as I said a couple of times already. But you can't say it too often at this early stage, alright? So, now, so they're both equal to r of t, so I'm going to write them set equal to each other, thus, axiomatically, and tilde, alright, and 3 plus ti, and we're going to, whoops, plus sign, we're going to equate components on the next line, right? Of course we are. So xi equals 3 plus ti, so x equals 3 plus t, and I'm going to call that bad boy equation 1, and you'll be blown away to know that I'm going to do the same in regards to y for the dropping the j components, right? So using simultaneous techniques, we could sub the result from equation 1 into 2, so let's do that. And first, but with equation 1, we've got x equals 3 plus t. We could make t the subject is actually handier, so subtract 3 from both sides in equation 1 and you'll get t equals x minus 3, and that's actually more useful. So subbing it in now into equation 2, we have y equals 1 minus, now we have 2t, but t equals x plus 3, so we sub in x plus 3. It's 1 minus 2x plus 6, which we could write as y equals negative 2x plus 7. So that particle has that path, and it's a straight line going down, quote unquote. So that's a little skill we need, and that's how we can convert from a vector function to the Cartesian function for its path in 2 dimensions. Finish off the video, we've got 2 examples here. So we've got to find the Cartesian equation for the graph represented by each of the functions given, where t is a real number. The first one there, so I've started off and we've got to let x equal 2 minus t, equation 1, y equals 3 plus t squared, equation 2. Okay, now writing like we did last time, equation 1 with t as the subject is handy to do, so I'm adding t and subtracting x. So I'm going to call that equation 1a because it's a modified equation 1. So sub 1a result into equation 2. So we have then y equals 3 now plus t squared, which would be 2 minus x all squared, which is 3 plus 4 minus 4x plus x squared, and that would be x squared minus 4x plus 7 would be our Cartesian path. X is a real number. Alright, for the final example we have here x equals 1 minus cos t, equating the I components, dropping the vector notation, y equals sine t, equation 2. Now this one's different. We have some trig valued functions there. Like last time, I'm going to rearrange equation 1 in terms of cos t. So we have cos t equals 1 minus x, equation 1a, modified equation 1. Now, using the Pythagorean identity, so that would be sine squared t plus cos squared t equals 1. We've got, using equation 2, we've got y squared equals sine t all squared, or sine squared t, as you know. Using the identity, sine squared t equals 1 minus cos squared t. Now subbing in the result for cos t, that would be 1 minus x all squared. Okay, so expanding and simplifying, be careful of the minus there, perhaps we could even do that. So it's a squared minus 2ab plus b squared, perfect square. So that minus sign in front of the square brackets changes the sign of everything, as you know. And we have negative x squared plus 2x, and the 1's cancel. So x is a real number and y equals negative x squared plus 2x, so that's parabolic. Okay.